Recently, I came across a paper about the confirmation of gravitational wave background existing in the fabric of space. India has also given its contribution in the international research by measuring millisecond pulsars in this experiment called Pulsar Timing Array. How does this all work? As these ultra low frequency gravitational waves are hard to detect. Okay, I haven't seen a paper that confirms the gravitational wave background, which would be startling if that happens, and nobody would be happier than me. So, what is this gravitational wave background? We are quite familiar, hopefully, those of us who are interested in physics, with the cosmic microwave background, right? Which is the leftover light of the Big Bang, the cosmic dawn, right? That's what it is. Now, what is the gravitational wave background? So, the early universe also produced gravitational waves, tremendous numbers of tremendous amounts of gravitational waves, and that should also be there in the background. Now, what are the things that can produce gravitational waves? First of all, cosmic inflation and the things that happen within cosmic inflation, that obviously can produce gravitational waves. uh, Primordial black holes and their interactions can produce gravitational waves. In today's universe, the merger of black holes, the merger of neutron stars, the mergers of neutron stars and black holes, and various such cataclysmic events can produce gravitational waves. Um, so you will have, and we know that gravitational wave exists. These waves exist. By now, we know that the first detection was in 2015, if I'm not mistaken, by LIGO. So we know these waves exist, but right now the technology that we have, it is such that we can only measure not waves but tsunamis. I'm talking about amplitude. See, waves come in various sizes, right? You've got tiny ripples, you've got gigantic waves, tsunamis. So right now we can only observe gravitational wave tsunamis. But I assure you there's a gravitational wave background out there with medium-sized waves, small waves, and then those tiny little ripples in space-time. And when we start detecting those ripples and those smaller waves, that's when we're gonna end up having a new set of eyes that will help us see the universe in a light that we've never seen. It's not light, it's gravitational waves. So we are familiar with the light, right? The light that we are familiar with, that is also waves, but it is electromagnetic waves. And similarly, there are gravitational waves. And we don't have eyes that can see gravitational radiation, but those waves do exist. We know that. So that is what the gravitational wave background is, and it exists in the fabric of space. It's everywhere, but we don't. It's too faint because, like we just discussed, the gravitational force is the weakest of the force. It is exponentially, hyper exponentially weaker than the closest weak force, which is the weak nuclear force. And that's why these ripples are so insanely hard to detect. Essentially, you would need to have a detector the size of the Milky Way to, to detect some of these effects and so on. Uh, so that's what it is. So I haven't seen any evidence of the confirmation of the gravitational wave background. I know it's there. We all know it's there, but the confirmation, no, it's not happened as far as I know. But I will look it up. I mean, I know the technology doesn't exist to confirm this. Okay. Now the other question is about millisecond pulsars and the pulsar timing array. How does this work? Uh, Ultra low frequency gravitational waves are hard to detect. All gravitational waves are hard to detect. Now, what are millisecond pulsars? What is this thing called the pulsar timing array? First of all, what's a pulsar? So a pulsar is a highly magnetized neutron star. What's a neutron star? A neutron star is a gigantic atomic nucleus. Just neutrons. Neutrons, that's it. It's a gigantic atomic nucleus. It's the size of a small town or something, but it has the mass of an entire star essentially inside it. And I'll not go into the way these objects are produced, but yes, you have neutron stars. Now, some of these neutron stars are extraordinarily highly magnetized. Okay. And they spin at a very high rate. And this magnetization of this property that it's highly magnetized, it ends up uh, doing something strange. The neutron star emits beams of highly energetic radiation, electromagnetic radiation, which is light, and whatever other forms of radiation in whichever frequencies, X-rays, gamma rays, whatever you want to call it. Yeah. So it emits two beams of highly energetic radiation in opposite directions, and it spins around its axis very rapidly. So that's a pulsar. Now, what's a millisecond pulsar? A millisecond pulsar is a pulsar whose period of rotation is less than 10 milliseconds. Okay? Less than 10 milliseconds. So that's a millisecond pulsar. And we can detect pulsars on Earth. I mean, some of them, their beams of radiation are pointed towards Earth. So we get these, and these are extremely highly periodic, beep, 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 but at a millisecond rate. Okay, you get that. And it's extremely precise. The timing is incredibly precise. Okay, these millisecond pulsars. So now that's what a millisecond pulsar is. Now, what's a pulsar timing array? So we have millisecond pulsars. We know a bunch of known such pulsars. And what we can do is we can have an experiment in which we detect an entire the pulses from an entire array of pulsars. Okay. Now, what that does is that if there is a gravitational wave that comes through that passes by, then there's going to be a very tiny discrepancy in the timing with which the pulse reaches you. And if this happens with multiple pulsars at the same time, and we know how it is correlated, then we know that we have detected a gravitational wave. And based on the anomaly, based on the discrepancy, we can actually determine the characteristics, certain characteristics of the gravitational wave. So that is the principle behind a pulsar timing array. And we have such experiments out there at work. Thus far, they have not detected gravitational waves. Thus far, all right. Maybe because our instrumentation and our the accuracy with which we make these detections isn't strong enough. Maybe it's not accurate enough. So there are reasons for this, multiple reasons that we can think of, and very plausible reasons. But thus far, we have not detected gravitational waves using a pulsar timing array. So that's what I know. I'm not sure about India's contribution in this. I have not read about that, and I have not read about the confirmation of a gravitational wave background. But I hope I have explained the concepts. What is the gravitational wave background? I've explained, hopefully. What is a pulsar? What's a neutron star? What's a millisecond pulsar? And what's a pulsar timing array? And how does it? Uh, how do such experiments, hopefully in the future, detect gravitational waves? So, yeah, there you have it.